Second. Second. Okay.
So hello everyone online. So today, welcome to today's seminar of Ecology and Evolution in Montpellier. So today the seminar is fully online. We are having Chris Bauch from Toronto, well, enjoy today's seminar, and I'll let Sébastien introduce today's speaker. Thank you very much.
Hello everyone. Okay, so it's my pleasure to introduce Chris for this same seminar. Chris did his PhD in mathematics at the University of Warwick under the supervision of David Rand in 2000. I think you were working on some pair approximation models, and I think that's the first I heard about your work at the time. Then you were a postdoc at McMaster University in Canada in the Department of Mathematics and Statistics. Then Chris has been an associate professor at the University of Guelph and is a professor at the University of Waterloo since 2013 in Canada. So Chris is a mathematical biologist and is interested in a wide range of topics from spatial population dynamics to infectious disease modeling. He's particularly interested in, I think, incorporating social processes into behavioral and epidemiological models, which is a really interesting and novel topic. And he also has worked a lot on vaccination, although I'm not sure you're going to talk about vaccination right now. And so it was a kind of a key common interest we had with our group and Chris. And so Chris wanted to make a sabbatical in Montpellier. Unfortunately, there has been a change of plans, but we're still lucky to have him giving the seminar today. So about tipping points in social-ecological systems. And Chris.
Thank you very much, Sebastian. So like Sebastian mentioned today, I would like to talk about tipping points in social ecological systems, and this is joint work with many people. Primarily my longtime collaborator Madhur Anand at University of Guelph, who is who's worked with me on most of these subjects. But you'll also hear a little bit about our joint work with Sonia concerning vegetation patterns. So what do we mean by a social ecological system? Well, we use the term to describe the coupling of two systems. Each has their own endogenous dynamics. So you have some environmental system which has it's evolving according to some dynamic, but you also have a human system evolving to some dynamic, and then you couple them together. For example, the human system might be a social system that's influencing some ecological systems through harvesting, or maybe restoration or protection. And similarly, the ecological system influences the human system not only through the economic benefits of harvesting, but also if there is a perception of conservation value or a risk of species extinction. And then within the human system, you might have a further feedback loop, for example, social norms, which might reinforce certain behaviors. That's shown in the lower right. So these have been studied for a while. So just to give you some context, perhaps the first person to think about populations mathematically was Malthus, who had the intuition that human populations grow exponentially, but yield is growing linearly, and so therefore they must eventually collide. Verhulst, of course, created the first logistic model that we recognize as such. And what's interesting is that this model wasn't intended for natural populations, which is maybe now the most common usage, but it was actually an attempt to model human populations in Belgium. and what the maximal carrying capacity of human populations was. And then later, of course, we had Lotka Volterra in the early 20th century, and then the first fishery models in the 50s represented human behavior as a fixed influence. But then over time, eventually, human behavior in these fishery models was represented endogenously, evolving according to its own dynamics. And more recently, we've had Eleanor Ostrom's work on fisheries and other systems, and also land use models in the 90s. So these are some of the systems that Professor Anand and I have applied this framework to. We've looked at coral reefs, forest pests, forest grassland mosaics, fisheries, and other systems, and I'll talk about a few of these today, maybe just some highlights in the interests of time. So one of our first systems was the Araucaria angustifolia forest grassland mosaic in southern Brazil. So in southern Brazil, there's this there's an endangered protected tree species called Araucaria angustifolia. You can see it in the lower left here. It has this very unique structure, and inland somewhat from the coast, it forms these forest grassland mosaics. So these are basically naturally occurring patches of grassland and forest, and this is a fire-mediated system because the fire generally, a grass fire generally will not penetrate far into these forest stands. So you had this kind of bistable system, and although elevational gradients do play a role, there is a tendency for the grassland to persist as grassland and the forest as forest. And so you had this naturally occurring bistability, and we started wondering in the early, I guess it was early 2013, 14, around that time, if you were to throw human influence into this model, how would that change the properties of the system? And human decision-making is important in this system because the grassland itself actually is very biodiverse, and it also has economic value as grazing land. And so you could suppose you could group humans into two categories. There are humans who are conservationists or non-conservationists, or you could say humans who prefer the grassland or humans who prefer the forest. So we can create this basic dichotomy, two types of opinions or behaviors, and then you can assume that humans respond to risk perception. For example, if the trees are threatened, they might say, well, these trees are becoming rare, we should protect them. So there's rarity-dependent perception. And then you also have social processes, which are very important, but which are often neglected in more economically driven approaches of behavior. So we know that humans learn from others, they're influenced by others, and they can learn new behaviors or opinions from others. So someone who prefers forest might become a grassland preferer, for example. And so in 2013, in Sci Reports, we looked at a model of this type of behavior. So this is the basic framework for how the humans behave. And I'll explain the motivating assumptions here in the next slide. But X is basically the percentage of individuals who prefer some state. Kappa is a social learning rate, so it's the rate at which individuals sample or talk to others. The X times 1 minus X basically comes about because there's frequency-dependent learning. So people are sampling others, and therefore the probability of talking to a forest or a grassland prefer depends on the frequency of those in the population. So that's where that quadratic term, X1 minus X, comes from. And then delta U is a utility function, which captures preferences. And in the lower right, we can see that the utility might be a function of mitigation, the cost of mitigation. So how much does it cost to protect the forest, for example? The strength of social norms is delta times omega. And so omega is 2 times X minus 1. So all this really means is that depending upon whether X is greater or less than 0.5, you will reinforce X equals 1 or X equals 0 behavior. So it's simply a majority enforcing mechanism. The norms tend to enforce whatever behavior is dominant in the neighborhood. And this is kind of like peer pressure. And then H times G of F is the response to the environmental state. So if forest becomes rare, then G of F might be larger. And so that might support mitigation behavior if X is the proportion of mitigators. So then you can take this X dot equation in the middle here, and you can couple it to, say, the forest equation. So in this model, the forest evolution was driven by a logistic growth function modified by a recruitment function. So this recruitment function, rho of F, is itself a sigmoid function because of the fire mediation. If forest is more dominant locally, then that will become a self-perpetuating loop, and you will be able to recruit more trees, and eventually you'll have a solid patch of forest. So rho of F is kind of flat, and then it shoots up, and then it's high again at higher forest. So this is what creates the bistability in the natural system. And then you have a mortality rate rho F, and then you have the harvesting function J of X, which depends upon how many people think the forest should be protected. So F is a function of X through the harvesting function, and then X is a function of F through the conservation value utility function U of F. So we have this fully coupled system, and that's just an example of this one of these systems. So I'll talk about some of the things we tend to observe in the forest grassland system and other systems. This is a very high level summary of what you observe with this framework, and some of the things are more obvious or intuitive, and others perhaps are surprising or make you think. So, for example, one observation we've had is that the presence of the human environment feedback and the social norms basically increase the number of states, the number of dynamical regimes and tipping points compared to the uncoupled system. And that's on account of the higher dimensionality. And we also find that if you assume rarity dependent feedback, so individuals are more likely to conserve a rare system, that will stabilize the environmental state because it's basically a negative feedback loop between the human and the environment. And so as a result, in these human environment systems, the environment system will persist for longer because humans will intervene eventually. We've also found that these social norms can be a double-edged sword. I'll speak more about this later, but this is a crucial factor and a crucial assumption about how you model norms. But the norms can either help or hinder the needed changes, meaning the sustainability objectives. And also the coupling itself can change the early warning of tipping points. So it can kind of mute or make the early warning signals ambiguous. So we have to deal with that challenge somehow. And again, I'll come back to that a bit later. Another example of a recent application is climate systems. So, of course, we know that anthropogenic climate change is an issue. We've gone past 1 degree of warming. The Paris Agreement is supposed to limit us to 1.5 to 2 degrees. And there have been numerous social movements around climate change that have influenced opinion. Some of them, as you might expect, are simply saying, well, we have to prevent climate change. Others are more complicated, such as the Yellow Jacket movement, which brought fuel prices into the mix. And the French audience members will remember this from some years ago. So we have these complex social dynamics in response to climate change, but also that are influencing opinion and action and sometimes policy. So the usual approach to modeling climate change is we come up with some trajectory about how CO2 will evolve over time and what the impact on emissions and temperatures will be. So, for example, we have the RCP scenarios ranging from 2.6 degrees to 8.5 degrees warming shown in the left here. And the colored lines are the emissions under those scenarios. And so you take those emission trajectories, you plug them into a very complicated geophysical model, maybe a generalized circulation model or an Earth system model, and you come up with the projections. So under these emission scenarios, this will be the projections out to 2100. So this is a useful approach, of course, but one thing it doesn't account for is feedback from the human system. And one way you can incorporate this feedback is through integrated assessment models, which attempt to capture economic influences and economic decision making. But there hasn't been so much work until recently on the other big driver, which is social processes, and I mean social in the broadest sense, including pressure that we may bring to bear on politicians, and also interactions between stakeholders and decision makers, between governments, for example. So in this case, we would then want, again, a fully coupled human environment system. So we might couple a social system to a climate system. So the social system, of course, they generate the emissions and they decide how many emissions to make, which emissions to make. And the climate system, well, we're seeing forecasts from that. We're seeing extreme events, and that's influencing the social system. And again, you can also have internal processes in both cases. So in particular, in the social system, you might have that learning again. You might have norms, which are very dominant. And of course, recently we've seen that norms, this is, this material from this talk is older, but now we've seen very vividly that norms can be a double-edged sword. Just because green technology is cheaper doesn't mean people will do it. If their norms are telling them don't adopt green technology, they'll stick with fossil fuels. So these processes are very important for driving climate mitigation. So how do we, what approach should we take to modeling these types of systems? And here, we think that the scale is crucial, and we have to be willing to move away from previous approaches that were geared more towards smaller groups. So to explain what I mean, is that sometimes we take a game theory prisoner's dilemma approach to greenhouse gas emissions. So the cooperation behavior is to mitigate climate change, and if you don't mitigate, that's like a defect decision in the prisoner's dilemma. And you could also apply this mentality to many systems, and in many systems it's a good one. But the problem is that framework assumes everyone agrees what a defect decision is. And that might be true in a fishery, where if Bob goes out at night or if he somehow is able to get more fish than the others, he knows he's defecting, he knows he's exceeding the quota. But for many problems like vaccine behavior and climate change, defectors don't see themselves as defectors. So we might want to use a different perspective. So perspective A is suitable for smaller systems like fisheries, end-person gains with ostracism, and everyone agrees on what defection is. But in our approach, we think this is more suitable for larger systems, where it's there's no people are more influenced by those around them. So the injunctive social norms, the norms that dictate what is good or appropriate behavior, these are more important. And this might follow more the voter model literature, where people are influenced by their neighbors. And in a spatial arena, this can form patches of one opinion or the other, as we see on the right here. So an example of a slightly older work is a simple social climate model, where for the climate system we used an Earth system model, where you have carbon transfer between the atmosphere, oceans, and vegetation and soil. And we use this model because A, it was simple, and B, it could replicate the RCP trajectories quite well if you calibrated it. And then for our social system, we again use the same framework of imitation dynamics. So individuals imitate others, they look at utilities, and if the utility is higher for a new opinion, they'll adopt it. And that utility is based on, again, social norms, the cost of mitigation, beta, the projected climate impacts, F of T. So individuals are extrapolating from recent trends to the future. Of course, and so here you see the equations. On the left, this is the simple Earth system model. So of course, we know that there are more complex climate models out there, but even the first climate models were very simple. And in fact, one of the first atmospheric models assumed a one-dimensional atmosphere, right? So we're choosing simple models because that's usually a sensible starting point to get an idea of what are the possible dynamics and what do we need to know next. And down the road, we can introduce more complex models as we learn more about the systems. So, and there is that coupling 1 minus x. So mitigation x reduces the carbon emissions C subatmospheric. And likewise, the atmospheric carbon goes into the temperature at the bottom here, dt by dt. And that temperature, the projections of the past temperature trends influence behavior through the f of t function, the response to temperature. And so a few of the things we've discovered from this are that the parameters, the social parameters, have a strong and asymmetric impact on the projected temperature peaks. So the social learning rate is particularly influential. It can change the predicted anomaly, global temperature anomaly, by 1 degree. And so these social effects are potentially very influential, and we need to pay more attention to them. The norms initially suppress mitigative behavior, delaying the transition to mitigation. And this paper is a few years old now, but now we, as I've mentioned, this is exactly what can happen in some populations. Reducing the mitigation costs can work, but the social learning rate has to be high. So if you want to achieve a reduced anomaly fastest, you have to both reduce mitigation and somehow promote social learning, support interaction between people of different opinions. And the global temperature anomaly is sensitive to the forecast horizon, which is more intuitive. So how far do people project ahead, or how far do they look ahead? The further they look ahead, the lower the temperature anomaly. And you can see some of the types of projections on the model on the left here. So we have proportion of mitigators A in the top for 2 different social learning rates. You can see how a faster social learning rate in green in panel A results in a faster uptake of mitigation. That results in panel B a more rapid drop in emissions. And therefore in panel C, a lower and earlier peak in the temperature anomaly, only at around 2.3 degrees. So basically what these social norms, these majority enforcing norms are doing is that because they're operating on more of a peer pressure type of model, if your mitigators are initially rare, then what this function w of x 2x equals 2x minus 1 does is that if x is initially low, it will tend to reinforce that behavior, so x will tend to stay low. Whereas if x is sufficiently high, then it will reinforce that behavior. So at a threshold of 50%, you'll either move up or down depending upon what side of that threshold you're on. And therefore, as we see in the lower right, greenhouse gases can either continue climbing if mitigation support remains low, or they could peak and then drop if mitigation support transitions to a high mitigation state quickly. So that's the double-edged sword that we're talking about. And this shows a parameter plane with net cost of mitigation on the horizontal axis and the rate of social learning on the vertical. And there you see that we can reduce mitigation. We can reduce the anomaly most quickly by both ramping up social learning and dropping the cost of mitigation. So the policy relevance is that to achieve climate goals, we can get a multiplicative effect. We can get more bang for the buck if we do more than one intervention at the same time. So that's a sample of some of our work on climate models, and we've since extended, and this seemed to attract some attention. The idea that social processes are important, and social learning in particular is important. This is how it was communicated in the media. Of course, sometimes the media are not always accurate, but one of our model predictions was that you need to interact socially to increase social learning, and that was spot on. And that comes across very clearly as a media headline. So we've looked at some extensions. I'm going to skip a few slides just in the interest of time. So we've looked at, so I'll go through the next few slides a bit quickly. We've looked at extensions like, what if you have a rich and a poor group? How does that affect dynamics? And we found that this kind of inequality can worsen the climate outcomes, can make the temperature anomaly higher. We've looked at, let's see, more recently, I don't have a slide for this, but we've looked at more structure in the system. So we have a regional model with five different land regions based on socioeconomics. And so we're basically trying to add structure to the human part of it to create eventually a more stratified and detailed model. And this is just to point out that you could also add climate tipping elements as well as social tipping. So we have many possible sources of climate tips: permafrost thawing, forest dieback, and these could also create this kind of S-shaped curve in the lower right that's associated with tipping. So in fact, both the social system and the climate system are subject to tipping points, and we've studied that as well. I will skip ahead. I'll just mention a few more examples briefly. So going back to the forest grassland mosaic, this is an example of the type of complexity that can emerge, and as a result, the increased number of tipping points. So for example, if you do a parameter plane versus conservation value of forest and grassland versus conservation value of forest versus grassland, we can see these multiple regimes. We might have, for example, limit cycles where grassland and agriculture oscillate. So individuals are either using the grassland as grazing or they use it for agriculture, and these kind of alternate over time in a cycle. Or you can have forest grassland limit cycles. So people aren't using the patches for the grassland for agriculture, they're just using it for grazing. But over long periods, there's an alternation between the forest state and the grassland state. So humans are actively modifying the system. They're turning that bistable system into something more managed. But in other parts of the parameter plane, you have equilibria, where you have the natural state of the system preserved as a bistable forest grassland mosaic. So for example, in the lower part, you have FGA in blue, which is some forest, some grassland, and some agriculture, which might be some kind of optimum in terms of providing some economic output, but also preserving the ecology. And that happens, interestingly, that happens when the conservation of grassland is on the lower side. So a lower conservation value of grassland stabilizes the dynamics, which again is one of these surprising results that can come out of these models and demonstrates their value. So this was a more recent paper we studied in 2016. And you can apply this approach to other systems like COVID-19. In COVID-19, the feedback was, again, behavior, but in the epidemic system, it was, you had social norms, of course. There were norms around masking and vaccines, and people were reacting to the prevalence of infection. And this created waves of pandemics. So the waves were also related to the emergence of new strains, but the second wave in particular was driven by relaxation of measures in the summer after the first wave, and you can model that process. We've used machine learning approaches to model it. We've used the previous approach of the social learning framework to address these questions and to study these waves. And these waves happen very naturally in the model, so they just fall out of the model. They're a very robust prediction of the model. And in some cases, they can have the models can have decent predictive power. If you try to fit the model to the first wave of the pandemic, you can do a decent job of predicting the second wave, according to our most recent results. And coral reefs is yet another system where we've analyzed this. So, for example, in the Caribbean, you have a couple of major players. You have the corals themselves. You have algal turf, which can grow over the dying corals. And if the algal turf is ungrazed, then it turns into macroalgae, so the plants, the larger plants. But they can be grazed by fish, and that can revert back to the algal turf state. And if the turf is grazed, then you can go back to live coral. So the fish play a large role in controlling and maintaining the corals. But also pollution and coastal development can harm the corals and promote this overgrowth of algal turf and macroalgae. And therefore, overfishing of parrotfish can become a problem in protecting the coral reefs, which are economically important and ecologically important for a lot of areas. And so in this system, again, you see very complex dynamics. For example, in the upper right here, in a plot of social pressure versus the parrotfish fertility or growth rate, you can see we have multiple states. In the upper left, for example, we have healthy coral unassisted, which means that the parrotfish are sufficiently fast growing that the coral can persist without intervention from humans. Whereas in the lower right hand, we have healthy coral assisted. So that means that you can have healthy coral, but you need some assistance to reduce the parrotfish fishing rate. So there have to be quotas or interventions that reduce the parrotfish harvesting, and then you can have a healthy coral. And then you have many other possible regimes as well. So that was the first part of the talk, was all about how coupling can increase the number of regimes we have. And with that, we have more tipping states. And the tipping states are interesting because they lead from one area to the other, and therefore they create a kind of a roadmap to sustainability, to some outcomes that we want to see. They can tell us, well, if we want to achieve healthy coral or reduce the global temperature anomaly, how can we do it most effectively? But of course, these are simple models, and the reality is that complication is out there, and we do have to deal with it somehow. So in addition to our big drivers between the environment and the system in green here, we know that there are other influences that come into play, other processes, both between the systems and within the systems. And these are very complicated to model. We often don't have the data, or the dynamics are so complicated that we can't get our head around it. So, the way I like to frame this question is how do we deal with the spaghetti with these very complicated feedback loops in our systems? And so in the second half, I want to talk about some ways that we can start to address this and pick apart what really matters in this messy spaghetti of interactions and feedbacks. And some of the methods, for example, include Cindy. So this is kind of a method of model discovery. I'll say more about it. Universal differential equations can be used, which is a machine learning dynamical systems hybrid, or also model reduction methods. So let's talk a bit about these. And the basic dichotomy here is inductive versus deductive approaches to modeling. So in the deductive approach, which is our dominant paradigm, we suppose or hypothesize some mechanism, we build a model, and then we test it against the data. And the models in the first half were all what you could call deductive. Whereas in the inductive approach, you choose some data set, you infer the model or dominant process directly from the data. And then so you're kind of creating or discovering a model directly from the data, and then you test the model out of sample to see if your discovered model works. And this is an example of Cindy. So Cindy is sparse identification of nonlinear dynamics. And the idea is that it's a process of repeated fitting of a large library of possible equations to the data. And in a series of successive steps, you try to whittle down this large library to a smaller, you could say, more readable library, a selection of classics, you could say, which best explain the data. And one of our papers was to apply this to infectious disease time series. And so, for example, here we see measles data from, this is, I believe, from London, and you can see in the red, we have the empirical data, and the infections occur every 2 years. So you have this nice peak every 2 years in measles data. We fit the Cindy model in green to this data, and the Cindy model discovered terms which we use in compartmental models. So for example, the largest weighted terms on the right are the S times I term, the cross term, and the beta SI term. So these are the mass action mixing terms that are part of the standard deductive models that we use. So Cindy seems to be discovering the same model that we know through our experience through the deductive approach is also useful. Another way we can deal with the spaghetti is by exploiting universal features of tipping points across various different systems. And of course, Vasilis Dekos at Montpellier has worked on this as well, as has Sonia and others. So this approach is based on a couple of mathematical theories that have been shown to be applicable to many systems. So the first piece of the puzzle is the central manifold theorem, which states that the dynamics of high-dimensional systems tend to converge rapidly onto a lower-dimensional subspace. So if you've got a 100-dimensional subspace, after a while, if you've got some differences in timescales, it could collapse down to, say, a 3 or 2-dimensional subspace, which is easier to analyze, which is very useful in terms of simplifying your dynamics. So a lot of dynamics happen on these manifolds. And then, moreover, if you're close to a tipping point, there's only a certain number of ways you can go through it for many systems. So you have these archetypes, these caricatures, or these normal forms of tipping points, i.e. bifurcations. And many different systems, regardless of what type of system you're talking about, they will often go through these bifurcations, and they exhibit similar behaviors going through these bifurcations. And so if you've read the early warning signal literature, you've read about critical slowing down, and this is kind of this cartoon is from Scheffer et al. And the kind of paradigm for that transition is you have a high resilience and a low resilience state. So in the high resilience state, it's resistant to perturbations, and that's what you see in subpanel A. And so the time series shows a very small variance in subpanel D. In subpanel C, it recovers very quickly from the perturbation. But then as the stability landscape is changing, you move to a low resilience state. And that means in subpanel E, you have a slower recovery, and subpanel F, you see a higher variance. So essentially what it means is that it's basically like a spinning top. You spin the top, and it starts to show these telltale signatures when it's about to tip. It starts to wobble a bit. And you know when the top is starting to wobble, it's going to fall over soon. So in this way, we know the system is going to go through a tipping point if we start to see this wobble, if we start to see an increase in the variance. And this has been applied to many systems: lake eutrophication, epileptic seizures, climate shifts, etc. And it's been shown that these different systems show this pattern of behavior. Now the problem with some systems, for example, the human environment or social ecological systems, is that the coupling can make these signals ambiguous. So, for example, this is the output of a simple forest human opinion model. And in A, C, and E, we have the time evolution of the forest cover as it's being pushed past a tipping point. And then in B, D, and F, we have the variance over time. Red shows the approximate location of the tipping point. And then the top row is a fully coupled system where we end up collapsing. You can see that in subpanel A, the forest goes to 0. In the middle column, it leads actually to an era of conservation. So the forest is conserved, but it oscillates. So there's some political swings or whatever. And then in the lower panel, we have the uncoupled system. So there's no human system the human system is not responding to the declining forest cover, and it simply collapses. And we see in all three of these cases on the right that the variance goes up. So if you're using variance as your indicator, you know something is going to happen, but you don't know what. It could lead to collapse. It could lead to an era of conservation. It could lead to a slower collapse or a more rapid collapse, depending upon the coupling. So what do we do if we see an increase in the variance, but we don't know what it's going to lead to? And this system has also been applied. This approach has also been applied to the climate system. So this is work by Dacos et al., showing that the climate system in previous in ice cores has shown this type of wobbling. So what do we do about this ambiguity? So with the last few minutes, I want to talk about data-driven dynamical systems approaches. So we know these early warning indicators, they may provide false positives. They can't tell us what type of bifurcation is approaching. In contrast, deep learning algorithms have achieved basically state-of-the-art in time series classification. So they can look at, for example, a time series of your pace or heart rate and they can tell you just based on this little blue time series here, are you walking, are you using the elliptical trainer, etc. So these deep learning algorithms might be useful for detecting critical slowing down and these subtle dynamical signatures close to a tipping point. In particular, we think the algorithm might determine the higher order terms that we normally throw out in these approaches. So the critical slowing down approach only uses the first term of the Taylor series expansion. The higher order terms, quadratic, etc., are thrown out. But there's information in those higher order terms, and there's information further away from the equilibrium. The shape of the stability landscape determines dynamics. But of course, analyzing these dynamics away from the equilibrium, it's harder and it's more system specific. So that's why we often don't look at it in our analytical approaches. Now, deep learning doesn't really care about that mess, right? It can find features associated with the stability landscape, the higher order terms. Sounds good. The problem is deep learning algorithms require lots of time series. You need thousands of cat pictures to get it to learn how to recognize a cat, right? And we don't have thousands of time series of vaccine scares or climate shifts. We don't have these for real world systems. So how can we use deep learning algorithms? Well, that's where the center manifold theorem comes in, right? So our hypotheses were that if we train a deep learning algorithm on a sufficiently large training set generated not from data, but from a diverse space of models that are going through tipping points, then the features of any empirical system approaching a bifurcation will be somewhere in that library. Well, what that means is that the algorithm will detect early warning signals in systems that are not explicitly in the training set. We only have the bifurcations in there or the random libraries of dynamical systems. The second hypothesis is that the deep learning algorithm will detect the early warning signals sooner than existing approaches and tell us what type of transition is occurring. So even a relatively limited training set, if we've formed it correctly, might contain the right kinds of features that characterize higher order terms and landscapes in real world systems. So we studied this with our PhD student, Tom Bury, some years ago. And I'll skip the methodological details in the interest of time, but basically we used a large library of random differential equations with noise. And then we used continuation software called Auto to search that space of models for bifurcations and systems going through a tipping point. And then we trained vanilla CNN LSTM deep learning algorithm to classify the stochastic time series from the random library based on the pre-transition portion. Fold, is it fold? Is it Hopf? Is it transcritical or branching point, or is it no transition at all? And then we took that, we trained it on the library, and then we tested it out of sample on systems where early warning signals have previously been studied to see if they would work as well for those systems. And so, like I said, it's a vanilla model, CNN LSTM. You have these two pieces. Long short-term memory is good at kind of remembering the previous parts of the time series, so it can look for those changes in dynamics over time. And the CNN breaks it down into smaller pieces, and that's a common image recognition approach. It runs convolutions over data to reduce it down to features that are driving the classification. So it looks for certain features associated with whatever you're studying. So we looked at 6 systems, 2 ecological models, a harvesting model, the consumer resource model from Rosenzweig MacArthur, and then a coupled behavior disease model, the SEIRX model. And then we looked at 3 empirical systems, a thermoacoustic system, whereby you change voltage and therefore create sound. It's a Hopf bifurcation. We looked at the paleoclimate shifts that were studied by Dekos et al. And then we also looked at changes in the oxic and anoxic states in the Eastern Mediterranean using data provided by Reichart and colleagues. And the thermoacoustic data was provided by Sujit and colleagues, R.I. Sujit. So this is an example of the type of output from the model. So these are the ecological models. The residuals are shown at the top here with just the variation around the mean for the fold, Hopf, transcritical, and neutral. And then panels rows 3 and 4 show the variance in Lagrange autocorrelation. So the classical measures, they show the variances going up before all of these and the correlation is also evolving, but not in the neutral case. And the second row is the deep learning predictions. So we see that you can have, it can tell you, I think it's a fold, or I think it's a hop. In the case of a fold transition, initially it's not sure, it thinks it's a neutral, but then as it gets closer, it thinks, okay, well, I think this is a fold bifurcation, and the fold probability in blue goes up. And then in the second column, eventually it becomes convinced that a hop bifurcation is coming in orange. In the third column, it eventually becomes convinced that it's transcritical. And then in the fourth column, it stays neutral the whole time. It doesn't think a transition is coming. So to rule out false positives, that's an important problem with machine learning. We use the ROC curve. So the ROC curve is a plot of true positive versus false positive rate. It's used, for example, in, say, COVID tests to determine if you're positive or negative, or many other medical tests. And the idea is you want to get a lot of true positives and minimize your false positives. And when you plot that on this ROC curve on the right, you should see something that is hugging the left and top of the curve. So you want a curve that's shoved up to the left and the top. And that means you have a high true positive rate and a low false positive rate. So we applied this to our 6 systems to figure out, is the machine learning algorithm giving us a high true positive rate and a low false positive rate? And here are the examples, for example, for the ecological models. So blue shows the machine learning working on the dynamical system library. Red is the variance, or orange rather, and green is the Lagrange autocorrelation for those 3 models. And you can see that it's working very well for the ecological models, much better than the variance or Lagrange autocorrelation. It's giving us high true positive and low false positive rate. And it's also predicting the right type of transition. In the thermoacoustic data, it also outperforms the standard methods, giving us a very high sensitivity and specificity. And also for the empirical data from the Eastern Mediterranean, from the sediment cores, we see that it's doing extremely well, much better than the variance and Lagrange autocorrelation. And the one where it's in terms of the disease model, it's interesting that if we're looking at the I variable, if we're monitoring infections, none of the approaches works well. But if we're monitoring the social system, for example, if we're monitoring social media, again, the machine learning algorithm can do well, and much better than the existing approaches. So that raises the interesting question, can we detect upcoming outbreaks by monitoring the social system? Or more broadly, can we monitor environmental systems by paying attention to social media? So that's an interesting possibility, because sometimes we have better data in the social media than we do for the environmental system in some respects. And that behavior for the SCRX model it's a feature of these systems that's called non-normality. I won't say much about it unless someone has questions about it afterwards. But the algorithm struggled with paleoclimate data the most. So this shows that in the case of the paleoclimate ice cores, all 3 approaches were kind of, they weren't doing that great. They're better than a coin flip. They're better than the diagonal line, but they really struggled. So lately we've been working on these climate systems, and we've tried to extend this temporal approach to a spatial temporal approach. We've looked at these easing models, which are models of magnetization. They're models of how a material can become magnetic as it's being cooled down if it's exposed to an external field. And in these easing models, you can see various types of changes. You can see both first and second order canonical phase transitions. And we asked the question, can we take an easing model, train it on the easing model and see if it predicts other systems? And so to do this, we trained the algorithm on the easing model, and we tested it on a couple of vegetation water system that's been studied by Sonia. We also looked at a sea ice percolation model, and we looked at CMIP5 simulations, which are climate simulations. And this was work led by our postdoc, Dan Diluski. And what we found was that for the vegetation systems, it worked pretty well. Both the spatial only indicator, the temporal only indicator, and the full indicator. It also worked well for the sea ice percolation model. And for the CBIC5 data, it only worked for some of the systems. So these acronyms are various types of models that go into the CMIP5 mix. I'll say more about it in a moment, but you can see that, for example, for GDFL, ESM2M, it worked pretty well. But for CSIRO, it doesn't work at all. So what's going on with that? Well, we realized that it works well for the CMIP models that concern terrestrial climate systems if we're using a second order phase transition, but it doesn't work well for the land cryosphere, atmospheric models, or the ocean cryosphere, the ice caps. So we had, so there's some progress in terms of these climate systems. And more recently, we've been trying to look at these other vegetation patterns like the Sahel, the Amazon, trying to see if we can predict vegetation patterns, and that's ongoing work. But the main thing, perhaps the main outcome here is that using machine learning on bifurcation libraries or dynamical systems, it provides a third axis, a third way of gaining evidence about climate change. So the first evidence axis on the right here is sophisticated mechanistic models like these GCMs, these circulation models. The advantage is that they're mechanistic and predictive. The disadvantage is that we don't know if we're including all the details. The other thing you can do is you can look at the ice cores. You can say, well, look at these paleoclimate shifts in the past. The advantage is that they're empirical, it's ground truth. But the disadvantage is that the nature of forcing is different from current forcing. So this third axis is qualitatively different what we're doing. We say that the information about the future climate states is already present in the noise we're experiencing right now. So the trick is to figure out how to recognize that noise and what it means. And we think that machine learning on dynamical systems might be able to help us with being able to read that noise. The pro and the con, of course, the con is that you need a big enough library with the right transitions in it. So we're kind of turning conventional wisdom about deep learning on its head. We're saying that you don't need 10,000 cat images. You just need an eigencat. You need an idea of what the true cat form is, and you can generate that with dynamical system, and then you can train the system on that. So it's a kind of a different way of using deep learning. So I think I'll skip to conclusions in the interest of time. So in the second half, we've seen that we can address the complexity of these social ecological states with inductive approaches. And in particular, combining machine learning and complex systems theory shows potential to provide early warning signals of climate tipping points. But there's much work to be done. We need to figure out what transitions are relevant and what deep learning algorithms are best for climate systems if we want to improve their performance. So that's all I wanted to say today. I'm glad to take a few questions if there's time for that.
Thank you very much, Chris.
Thank you.
And yeah, we do have 10 minutes for questions. So people online, don't hesitate to raise your hand. I'll give you the floor to ask your question. And meanwhile, people are thinking of potential question. I had one on the first part of the seminary, the one on modeling the coupling between social and biological systems. I was wondering, there is you put a function that captures imitation game that you favor the most common, but I was wondering how you define the distance between players. Is it spatial? Is it based on social status? And a follow-up question is, can you account for the emergence and the new role of social networks like Facebook and stuff like that can implement connections much farther than just the new neighbors in space?
Yeah, so in terms of the models we've looked at, they range from the very simplest model, which assumes no space and homogeneous mixing in the population, to more sophisticated models on social networks, which assume that people have a network, they're influenced by their network. That network might have some structure to it. There's a degree distribution, etc. So the same types of processes can be applied in models of different structure in that way. So in the social network model, you're influenced only by your network neighborhood, and you talk to them only. And in terms of social media data, we also have a few models trying to use the social media data to inform the model structure. And, to give you one example of an interesting problem there, we know from social media data that often the dynamics, they're not always like a Gaussian distribution, right? They're heavy tail distributions, whereby usually it's relatively quiet, and then a celebrity will tweet something, and there will be a massive burst of activity. So these distributions are fat tailed, and so our methods, early warning signals, etc., they usually assume this kind of Gaussian white noise. So we have to adapt them to that situation. So we have a few models looking at how does that change dynamics. So yes, but the shorter answer is that we've looked at various ones, and it is possible to kind of do this on social networks, which we've done for a few models, often with multiple layers. So you might have a physical layer through which some disease is transmitting, and then you have an ordinary social layer, which is people talking to their neighbors, and then you have the social media layer with more distant connections, talking to your uncle who's in a different country or whatever. And they're all coupled together, but there's 3 layers. It's called a multiplex network, and those are receiving a lot of interest lately as well.
Okay, thank you very much. So
We have 2 questions. One is from Sylvain Gandon. So I will give you the right to.
So Sylvain, can you hear us and can you talk? Yeah.
Usually.
Oh, he disappeared.
It's okay or not?
That's right.
Can you hear me? Yes?
Yes.
Yes.
Okay. So thank you, Chris, for your talk. So I had a question about the second part. So maybe it's a very naive question. So you contrast the deductive and the inductive approaches. And I was wondering whether you can use the inductive approach also to improve the models, the mechanistic understanding of the processes that we are studying. So I find it very convincing what you showed to predict catastrophe, for example, but I find also that the deductive approach and the mechanistic understanding or models that we build are also very pleasing, when very satisfying in a way. And I was wondering whether you can also use the inductive approach to improve those mechanistic models.
Yeah, thanks, Sylvain. That's a great question, and of course, that's an issue with machine learning, is that it can be a black box depending upon how it's used. And I like to use the analogy or the story of AlphaGo, which was the computer, the AI that defeated the best human player. And so these AIs can beat the best human players in games like Go and chess. But what we've also observed is that human players have learned new strategies from watching these AIs play. And so the human play is influenced by learning from what the AI is doing. And that's my analogy here. We're looking for a gray box. So to use the example of Cindy, that algorithm, that approach can discover terms from the data. And the way I see that being used in the future is that Cindy can tell us which terms are important, and maybe it can discover terms that we haven't thought of before. Maybe there's some small term that maybe it's not as important as mass action mixing, but it's somehow relevant. And in that way, we can focus in on those terms and study them more carefully to gain that intuition that we really want and that we need. And that, as modelers, we find so satisfying that would give us that kind of insight. So I agree that we don't want to, we don't want to use it as a black box, and there are ways to avoid that in these approaches.
Okay, great. Thanks.
Yes, we have one last question from Sebastian.
Yeah, I had 2 quick questions. One was, I think most of the models of where you couple ecological dynamics with social dynamics, they formally they really look like the social dynamics model is often take the form in the example you showed of a kind of replicated dynamic. So it's very close to a kind of couple eco and evo model. So I was wondering, my first question was like, have you try or have you plans to try to use this kind of approach to apply this to the eco-evolutionary dynamics of system, which could also affect like things like early warning signs and so on? And the second question was, you mentioned something about non-normality of ecological dynamics that was important, and you said you could say more about that, and I'll be interested to hear more if it's not too long about that.
Sure. Yeah. Thanks, Sebastian. So, yeah, the first question, the shorter answer is I haven't looked at it yet, but I think it's a very interesting possibility. And if you've got replicator dynamics in the natural system, and you've got this imitation dynamic in the human system, dynamically it could be very interesting. And of course, as you're aware, the imitation dynamic, it looks like a replicator dynamic because that's where they got the idea from. They said it was a bit like the idea of memes that are spreading. So people are kind of learning behavior. The more fit or the more attractive idea is what spreads, in much the same way that a better viral a mutant can spread if it's better at surviving. And then your second question was about, sorry, remind me the second question again.
Yeah, it was, you mentioned something about the fact that there was something about normality of non-normality of ecological dynamics.
Yeah, that's right. Yeah. So that in that system, that model, that was a behavior disease model for childhood infections. So the non-normality basically there comes from the fact that vaccination, it happens once when you're young, and then you're good for the rest of your life if you're talking about measles or rubella vaccine, for example. But the decisions are evolving more quickly. So I might be vaccinated when I'm a toddler, but my opinion about vaccination can change more frequently throughout my life. So even though I can't become unvaccinated, I might be more hesitant about the vaccine in 5 or 10 years, or even next year. So it's the timescale difference that comes into play there. That generates the non-normality, which means that you can see the signals in one variable but not the other. Although that may also depend upon the noise, because if the noise is set correctly, you should be able to see it in both systems by the Tockins embedding theorem. But it might be easier to see in one rather than the other, depending upon how much noise is present.
Okay, thanks.
Okay. So thank you very much, Chris. And you have it's time for the end of the summary. It was really nice having you from Canada. And to people online, thank you for coming, and see you next week for our next seminar.
Yeah, thank you very much. Au revoir.
Thank you, Chris.
Thank you.
Okay, thank you.
Yeah, thanks, Youssef. Thanks, Enya. Good to see you, Sebastian.
Yeah, good to see you. So
okay, have a good
have a good day. Bye-bye.
Yeah, thank you. Bye-bye.